Sheltering megalithic temples in Malta, evaluating the process through the data collection and modeling. Outline of this presentation includes the introduction to megalithic temples of Malta, decision to erect the shelters, weathering processes, objectives of the study, landscape topology and terrain, fluid simulations, issues with the computational fluid dynamics modeling, multi-scale domain approach, verification and validation, and summary and conclusions. The megalithic temples of Malta are freestanding stone structures which started being constructed around 3500 BC and continued being used until 2500 BC. These sites have been included in UNESCO World Heritage List as the megalithic temples of Malta. The Hajarim and Mnidra complexes were covered by the protective shelter in 2008 and 2009, and this after much deliberation with the aim of slowing the deterioration process affecting the sites. Tarshin temples were also protected by the means of protective shelter in 2015. These protective shelters have already shown conservation-related benefits with the elimination of periodic collapses of megaliths, such as those which had occurred after heavy rain in Hajarim and Mnidra, and periodic flooding of Tarshin temples. The decision to erect the shelters are mostly related to the material problems, including flaking, powdering, severe loss of the surface material, as well with the structural problems, including collapses caused by loss of infill and reduced load-bearing capacity of severely weathered megalith. Open-sided shelters within a lifetime of 25 years considered to be the best option in order to address some of the principal causes of deterioration, including direct rainfall, salt weathering, and thermal stress. Weathering processes are directly related to the climatic parameters inside the temples. These parameters, such as rainfall, wind, solar radiation, temperature, and relative humidity, are interlinked with each other. Thus, weathering process becomes even more complex. These processes are identified mainly before the installation of the shelters at the Hajarim, Mnidra, and Tarshin temples. Nowadays, thanks to the action of the shelters, the main problems related to the direct and indirect action of the rainfall and solar radiation are for the most part attenuated or even eliminated. Nevertheless, salt cycles are to be carefully monitored and investigated, as well as relative humidity and temperature fluctuations, in addition to the wind action to megalithic surfaces in the new microclimate created by the shelter. In order to evaluate these processes and final impact on the temples, the numerical simulation approach was chosen. With integration with in situ measurements, the aim is to answer the questions how these shelters affect the microclimate and the megalith themselves. The objectives of the study is to outline a principal methodology using computational fluid dynamics to study conservation problems related to the archaeological and historical structures, as well to use this methodology to evaluate the effects of the shelters over the Malta's megalithic temples through the analysis of the wind velocity, temperature, and humidity distributions. In order to reach objectives through the numerical modeling, first of all, we have to evaluate the global terrain. Simply because the temples of the Hajarim and Mnidra are located in the southwest coast of Malta, where because of the complexity of the terrain, a slight change in wind speed or direction could completely change the wind flow patterns in and over the temple. Thus, it will affect simulation accuracy of the interlinked weathering process. Because of high resolution grid, which has to be used in order to accurately resolve the solution inside the sheltered and unsheltered temple cases, which would lead to very high computational cost, A different simulation approach is being proposed in the three stages: macro, meso, and micro, where in every stage previous simulation results are going to be used as an input for the next stage. Of course, we have to consider the errors and uncertainties of the simulations. Therefore, model verification and validation has to be taken into account. When we look at the numbers of publications related to computational flow dynamics studies for heritage science, we can see the growing trend, which shows the relevance and the growing interest for these types of studies. Halls, churches, exhibition spaces, and galleries are the most usual and common subject of computational flow dynamics studies in heritage science, while the larger areas like historic villages, city centers, and large building complexes are not so common. The majority of papers that describe fluid dynamics simulations in cultural heritage are related to the air movement and the resulting ventilation of spaces, most of which are indoors. There are studies which address turbulence modeling issues related to the simulation of flow over complex terrain using coupling between numerical weather prediction code and the classical CFD code. The main applications are wind farms and wind energy and urban air pollution. But substantially there are low in heritage science, as the some part of the methodologies could be more applicable to heritage science applications. There are three main domains, which are identified as a macro, meso, and micro. The macro domain represents the terrain, the global domain basically. The meso domain is representing the temple, and the micro domain representing the surface of the temple. General representation of three-stage computational fluid dynamics data flow approach is shown here, where in every step validation has to be done, as well in all of the stages model verification has to be passed. In stage 1, which represents environmental conditions over the terrain, verification and validation of the pseudo-transient simulation will be performed, which will represent the seasonal, monthly, or day-night cycles of the wind speed and direction, temperature, turbulent kinetic energy, dissipation rate, turbulent density. These simulation results will provide additional information which will be used as initial conditions for the mesoscale in stage 2. In stage 2, with the mesoscale, the pseudo-transient or transient simulations will be performed, which will represent environmental conditions inside and around the temple. In this stage, the more accurate and detailed information about the local wind flow magnitude and direction inside the temples is obtained. By integrating additional environmental data like temperature, humidity, solar radiation, more realistic representation of the microclimate inside the temple will be achieved. These simulation results will provide more representative timescale data, which will be used for the correlation with experimental data of in-situ analysis using portable instruments. These instruments like 6RD XRF, Raman, FTIR, or thermal imaging. The aim of the stage 2 is to provide valid answers to what are the main causes of the specific deterioration issues inside the temple. In stage 3, in the microscale, the aim is to study the processes near the wall. In this stage, integration of the discrete element method with the computational fluid dynamics is being proposed in order to study mass and energy transfer between solid surfaces and surrounding environment. thus in salt deposition, salt cycles and crystallization dynamics, condensation, erosion, and infiltration.
So in terms of the boundary conditions used in the model, we used not only guideline papers from the literature for the specification of, for instance, the inlet boundary condition or the outlet boundary condition, but we also used best practice guidelines in relation to CFD simulation of flows in the urban environment. And this was in fact a major outcome of cost action 732. The problem with these guidelines is that they're mostly focused on urban environments which are not really reflecting the current situation that we are modeling. So this was a limitation, but these are the only guidelines in existence which approximate or come close to the situation that we are actually modeling. So the specifications of certain, for instance, domain dimensions, boundary conditions, or even discretization of the problems are all specified in these guideline documents. And we actually adopted what is specified in the guideline document into our modeling approach. In terms of verification and validation, we plan to perform various types of testing, including verification and also validation. In terms of verification, we'll be studying grid convergence, that is, making sure that the solution is independent of the grid that is being used, and also, of course, residual and variable convergence. By variables here we mean the variables of interest, particularly velocities as well as temperatures. Later on, we're also planning to validate the model itself using various types of measurements on site. These will include measurements of velocities in 2D and 3D using ultrasonic flow anemometers. We'll use also LiDAR flow measurements, particularly to investigate the inflow condition on site, that is, the wind velocity variation with height. We'll also be adopting environmental stations at various locations on the site, internal sensors within the internal environment of the temples, and also thermal imaging. And all of these will be combined, let's say, to ensure that our model is reflecting what is happening in reality. The situation is very complex, therefore we need a multitude of sensors operating simultaneously in order to provide not only the correct boundary conditions, but also data which can be used then to validate our model. So in conclusion, the aim of the paper is basically to propose a multi-scale domain approach in the CFD study of megalith temples. The approach promises to be more accurate because we consider different scales of flow with a certain level of detail. So we start with the macro domain, we go on to the meso domain, that is basically the temple area and the near vicinity of the temples, and also later on we're also planning to go into the micro domain where we study individual megaliths. So the model itself will be used to provide a representative simulation environment that is faithfully representing what is happening on site. And therefore, such a model will be able to provide guidelines on perhaps mitigation measures in order to preserve the integrity of these sensitive sites. Finally, the methodology can also, or hopefully will also be used in order to provide guidelines which are more specific to the current problem which we have. That is, whereas we have guidelines for the simulation of built environments in urban contexts, we want to have models which can be used as a benchmark or as a guideline in order to provide further studies with the possibility of making use of such guidelines in sensitive sites such as megalithic temples or historic structures.